speaker today is Vaidy Sivaraman, and he will speak on polynomial chi-boundedness.
Okay, thank you, Sandra, very much for the invitation. And I'm very sorry. I think there was a problem with the time difference. So Mississippi is 1 hour behind. And on the website, it said like 1 p.m. clock our time. But anyway, very sorry about that. So I'm going to talk about polynomial chi-boundedness. So the two main invariants in this talk. So this is a topic in graph theory. So we are going to talk about graphs. All our graphs are finite and simple. So no loops, no multiple edges. And it's the story of the relationship between two invariants. And one of them is the famous chromatic number. So you want to color the vertices of your graph so that if there is an edge, the endpoints of the edge must get different colors. That's the only restriction. And of course, the smallest number of colors you need is called the. So this started in the four-color theorem, but it was Brooks who kind of separated that from a topological context and just did it for abstract graphs. So for any abstract graph, you can define this without a map. And Dirac, in his thesis, had a lot of results about chromatic numbers, and Galai. And so from there on, there has been a steady research line about the chromatic number. So this is a little picture of Francis Guthrie, who kind of started the four chromatic, the question of whether every planar graph can be four colored. And it's arguably, you can say it's one of the most famous graph invariants. It's very mysterious because we can't answer this question. What causes large chromatic number? So we can tell when the chromatic number is 1, precisely when there is no edge. We can tell when the chromatic number is 2, when there are no odd cycles. That's the famous class of bipartite graphs. But other than that, it's very hard to say something definitively, although there are a lot of results along these lines. So the one thing that I will not talk about is a different line involving the chromatic number, probably the most famous conjecture in graph theory, the Hadwiger conjecture. And it says that it's not precisely answering the question of what causes large chromatic number. It's the reverse implication. So it says if your chromatic number is k, then you can delete vertices, delete edges, and contract edges and get a complete graph on k vertices. So that's what Hadwiger's conjecture tells you. And the other invariant that is part of the chi-boundedness story is the clique number. So you have a set of vertices so that between any two there is an edge. So that's what is a clique, inspired from social studies. And the largest size of a clique is the clique number. And it's obvious that if you have a clique of size k, you need at least that many colors. So there is an immediate relationship between these two. The chromatic number is at least the clique number. But what else can we say? If the clique number is 1, the chromatic number is 1. But if the clique number is 2, then you can't even tell what the chromatic number is. So that's a standard thing that you do in an undergraduate course in graph theory. You teach the Michalski's construction. Such a graph, it increases the, but it keeps triangle freeness. It preserves triangle freeness. Better constructions in some sense of others, but the final, the main theorem, fundamental theorem of chi-boundedness is the Erdős theorem, which says that you can have graphs with arbitrary large girth and arbitrary large chromatic number. So that's fundamental to the theory, as we will see. Okay, let's start by a little review of the early results. We say a graph is H-free if it has no induced subgraph isomorphic to H. So one of the first results along these lines was that if you have a line graph, then the chromatic number is at most the clique number plus 1. And Sensei in 1974 proved that if you don't contain a path with 4 vertices, P4 means a path with 4 vertices as an induced subgraph, then the clique number and the chromatic number coincide. And Wagon in 1980 proved that if you don't have 2K2, so 2K2 is the graph with 2 edges and 4 vertices, in which every vertex has degree 1. Then your chromatic number is at most omega plus 1 choose 2. So it's a very simple counting argument. So it's a very nice proof. So these two are very nice. I mean, the second and third are actually easy to prove. And these are the 3 results that started this analyzing the relationship between chromatic number and the clique number. And so inspired by all this, where he said, let's systematically study graph classes and study what's the relation between the chromatic number and the clique number. And his main result in the paper was that if your graph has no T vertex graph as an induced subgraph, then you get this bound. But the problem is it's exponential. So ideally, people want to reverse this. They want to switch the T and omega. They want to switch T and omega. Biggest open problems in the area. You want to be able to say that the chromatic number is at most omega times T. So, okay. So even before all these results, Burge was interested in graphs that have the chromatic number and the clique number to be equal. And he realized very early on that that is a very, very loose condition to stipulate. So he said, to make it nice, he requires the property for all induced subgraphs. So this is one of the most fruitful definitions in graph theory. The graph is perfect if the chromatic number and the clique number are the same for every induced subgraph. And why are they important? Well, a lot of classes that we study, bipartite graphs, comparability graphs, caudal graphs, all of these are perfect. So it kind of puts a single framework in which you can study graph classes. So the study of graph classes started with the definition of perfect graphs in some sense. And Lowas, when he was 22, proved that the complement, if you take a perfect graph whose definition doesn't say anything about the complement, you take the complement also satisfies the definition. So this is a very, very nice theorem. And recently, Laszlo Lowas and Avi Wigderson received the Nobel Prize. And this theorem was mentioned as part of the citation for Laszlo Lowas. So very nice result. And with Grotschel and Alex Shriver, he also proved that they have very nice algorithmic properties. So that's another reason to study them. Suddenly requiring such a property, you can design algorithms that are polynomial type, like for stable set, for chromatic number. So you can find the chromatic number of a perfect graph in polynomial type. So that's their theorem. And the final thread in the story is the solution of a very hard problem, determining exactly obstacles for perfection. So it's easy to see that odd cycles and their complements of length at least 5 are obstacles, but these are the only obstacles for a graph from being perfect. So this you should compare it with the Kuratowski theorem in planarity. So graph is planar if and only if it has no minor isomorphic to K5 or K33. but the difficulty in the proofs are of different levels. But I think it's of the same flavor. There we are doing minors, here we are doing induced subgraphs. Okay, so what if graphs are not perfect? Still, can we say something if there is a close relationship between the two numbers? And he made a nice definition. You take a hereditary graph class, which means graph class such that you take any graph and take any induced subgraph of it, then that graph is also in the class. And an induced subgraph is one where you just delete vertices. So I should have told that a long time ago. Maybe I did. So an induced subgraph of a graph is obtained by just deleting vertices. You can't delete edges. So that's the definition of induced subgraph. And he said its graph class is chi-bounded if for every graph in the class, the chromatic number is some function of the clique number, some function of the clique number. So that's his definition. So immediately you can ask some natural questions. Suppose somebody gives you a hereditary graph class, you can immediately ask, is it chi-bounded? So that's the first question you can ask. And if so, is there a function is there a polynomial function that will be a chi-bounding function for the class? So polynomials are very nice. I mean, mathematicians love polynomials for several reasons. I mean, it gave rise to a lot of algebra analysis, algebraic geometry, and there is a polynomial method in combinatorics, polynomial time algorithms. So polynomials are the favorite functions to think about. And so very natural for approximation algorithms to have polynomial chi-bounding functions. And then if you have one, then you start to talk about the degree of the polynomial. You want it to be as small as possible. So the question is there a linear chi-bounding function for the class? And another question would be to find the optimal chi-bounding function for a class. Find the optimal chi-bounding function for a class. So these are four very natural questions to ask about any graph class that is closed under taking induced subgraphs. And so Gaffars made a lot of conjectures, and these were recently solved by Paul Seymour, Alex Scott, and Maria Chudnowski and Sophie Sperkel. So let me mention three theorems. So a hole is a cycle in a graph of length at least 4. That's also induced. So it's an induced cycle. The hole is an induced cycle. And the first result that they proved is if you exclude all the odd holes, holes of length 5, 7, 9, and so on, then you get a chi-bounded class. This result is a standalone result. It doesn't depend on anything. So it's a very, very nice paper. This is, they do some clever arguments and it doesn't depend on anything. It's a completely standalone result. And then they proved that for every t, if you exclude all holes of length at least t, then it's still chi-bounded. And putting these two results together, they were able to show that it's enough to exclude holes of odd length, at least t. So just excluding odd holes from a particular t is enough to force chi-boundedness. And they even strengthened this theorem, the third theorem. But I'm not going to go into that because the main purpose of the talk is to talk about polynomial chi-bounding functions. So, and none of these give you a polynomial chi-bounding function. So their proofs, all of them give you something that's exponential. So, and why are we interested in polynomial chi-boundedness? A good reason is for another famous conjecture of Erdős-Heinem. So for every graph, if you exclude that graph as an induced subgraph, then you get very large stable So there's a famous conjecture, and if you have a polynomial chi-bounding function, it immediately implies the Erdős-Heinle conjecture. So it goes only one way. It doesn't, just because Erdős-Heinle conjecture is true, it doesn't mean there is a polynomial chi-bounding function. In fact, it doesn't even mean there is a chi-bounding function. So, and here is a nice conjecture that whenever you have a chi-bounded class, it's polynomially chi-bounded. Whenever you have a chi-bounded class, you have a polynomially chi-bounded function that will be a chi-bounding function for the class. So it's not clear how this conjecture is going to go. Which way is it going to go? Is it true or false? Proving it to be true is going to be very, very difficult, because it's about every chi-bounded class. A counterexample is slightly more promising, because you just have to take one polynomially chi-bounded class and show that there are graphs, so that there is a sequence of graphs and where the dependence grows more than a polynomial. But even that looks hard. So we have no idea about this conjecture, but it has forced some research in this area. And the classic question about chi-boundedness is the Garfar-Sumner conjecture. Any forest, a forest is a graph without cycles. Any forest you exclude, then the class you get is chi-bounded. Why should we exclude only a forest? Why not an arbitrary graph? Well, if your graph has a cycle, say of length k, then you can appeal to the Erdős fundamental theorem. There are graphs with arbitrarily large chromatic number and no cycles of length k. So for a graph G with a cycle, the class of G-free graphs is not chi-bounded. So that's the power of Erdős theorem, whose proof was initially probabilistic. And so this gives a nice characterization of forests. A graph is a forest if and only if you exclude, the resulting class is chi-bounded, if the Garfar-Sumner conjecture is true. So that's why a lot of people are interested in this. It tells you something about cycles in graphs. And there's a very hard conjecture as well. A lot of partial progress has been made on this. Let me mention one result about polynomial chi-boundedness. Here, we are just going to loosen the induced subgraph definition. So local complementation is when you take a vertex, it has neighbors, and you just take the subgraph induced on the neighbors and just take its complement. That's called a local complementation. And the vertex minor is a combination of local complementation and vertex deletion. And with Kim, Kwon, and Sangil, we proved that if you don't contain a cycle as a vertex minor, then you are polynomially chi-bounded. So, but this was generalized by Bonamy and Filipchuk to say that if you have bounded clique width, then you are polynomially chi-bounded. This was a very nice result which appeared in Advances in Combinatorics. And the reason we were interested in excluding a cycle was there was a general conjecture that any graph you exclude as a vertex minor is chi-bounded. And that was open for a while until a student of Jim Gielen proved it. James Davis proved this theorem, the conjecture of Gielen. So that's not a conjecture anymore. So any graph you exclude as a vertex minor is chi-bounded. So that immediately suggests a natural conjecture. How about, is it polynomially chi-bounded? So any graph you exclude as a vertex minor And a vertex minor is just a combination of two operations, one of which is the deletion of a vertex, and the other one is this strange looking operation, local complementation. So you're complementing, but locally. Just take a vertex, just complement in the neighborhood of a vertex. And so another thing I wanted to talk about was, how do you prove chi-boundedness results? How do you prove that a graph class is chi-bounded? Well, the standard thing is to do induction on the clique number. So you assume if k is the clique number of your graph, whenever it's k minus 1, you have bounded chromatic number, and somehow you want to take your graph and break into pieces so that the clique number drops from k to k minus 1. And it's about breaking into pieces that works for a lot of things. And another tool people use is what is called the leveling argument, which I think has been used before in graph theory, but not in a systematic way. It's what everybody knows. You take a vertex, you just classify vertices by distance from that particular vertex. Let's call it the root of the graph. So vertices at distance 1 is called level 1. Vertices at distance 2 from the root are called level 2, and so on. And the nice fact is that you can give the same colors to vertices in odd levels and vertices in even levels because there are no edges between them. So that's what is leveling argument, and there have been several variations on that. So with Maria Chudnovsky, we were able to prove that if you exclude the path on 5 vertices and cycle on 5 vertices, then the graph is 2 divisible. 2 divisible means you can break your graph into the vertex set into 2 parts, so that the clique number of the graph induced in each part is smaller than the clique number of your original graph. And what has that to do with the chromatic number clique number relationship? Well, you can do it again. So if your clique number is k, you can break into 2 so that the clique number becomes k minus 1. That you can break into 4 with clique number k minus 2 and keep on doing this. So, which means that the chromatic number is at most 2 to the k, where k is the clique number of the graph. So it immediately gives a bound, but unfortunately it's exponential bound. So 2 divisibility is a property which gives you chi-boundedness, but not polynomial chi-boundedness. And another thing we proved was if you exclude P phi and a graph called the bull, a bull is a 5-vertex graph obtained from a triangle with 2 edges hanging off at different vertices. Then you get what is called perfectly divisible, which means one part is perfect and the other part, the clique number, has gone down. So these are the 2 notions of divisibility here. Break your graph, vertex set into 2 parts. Either the part is perfect, in which case chi is omega, or the clique number has gone down. So with different combinations, you get different kinds of divisibility. And there is a nice conjecture of von McDiarmid which says that 2 divisible graphs are just odd hole free graphs in disguise. They're the same. A graph is odd hole free if and only if it's 2 divisible. So this is a nice conjecture. Recently, there was a breakthrough that odd hole free graphs can be detected in polynomial time. So if this was true, if this conjecture is true, then 2 divisible graphs would also be recognizable in polynomial time. But we still don't know that. So, okay. So how about excluding 2 graphs? How about excluding 2 graphs and a finite set of graphs? So here there is a good amount of literature, and there's a very nice survey by Schiermeier and Randrath who talk about all the results that we know up to date. So one classic result is one that Remember the Vaidy's theorem? If you have a line graph is a graph obtained by excluding one of the 9 forbidden induced subgraphs. So that's his theorem. A graph is a line graph if and only if it doesn't contain one of the 9 graphs. And of the 9, these are 2 of the 9, K13 and K5 with an edge deleted. So we saw that Wiesing proved that line graph has chi at most omega plus 1. So combining Vaidy and Wiesing, we get that if you exclude those 9 graphs, then you get chi is at most omega plus 1. But what Kierstead was able to show is that you just need to exclude 2 of them, not all the 9, to get the bound. You just need to exclude 2 of the 9 graphs to get the bound. So this is a very, very nice theorem. And along similar lines with Katie Cameron, Shenbei Huang, and Irina Penne, we were able to show that with some combination of paths and cycles, you get chi is at most 1.5 omega. So again, so this is an attempt to try to prove the polynomial chi-boundedness of PT free graphs. As I mentioned, even P5 free graphs is open. We don't know whether P5 free graphs are polynomially chi-bounded. So, but here what we are able to show is that if you assume C4 and C5 free, then it's polynomially chi-bounded even for P7 free graphs. So this goes through a structure theorem. So we actually give a structure theorem for such graphs, how to build all these graphs, and then use that to prove the polynomial chi-bounding function. So that's a big difference between chi-boundedness and polynomial chi-boundedness. For chi-boundedness, leveling arguments are good, 2 divisibility is good, but those things are not good for polynomial chi-boundedness. So a lot of polynomial chi-boundedness use either a structure theorem or this perfect divisibility is okay because it gives you a quadratic chi-bounding function. And here is a nice problem. If your graph has no P phi and no C phi, can you prove that chi is at most omega squared? In fact, it is quite possible that if you have P phi and C phi free, you might be able to partition your vertex set into omega perfect sets, omega parts where each part induces a perfect graph. Then each part you just need omega colors. There are omega parts, so you can just do it with omega squared colors. So that's the conjecture. And recently, I've been interested in the fork-free graphs. So what is the fork? It's also a little tree. It's one of the smallest trees. So when you teach an undergraduate graph theory course, you list all trees on 4 vertices, 5 vertices, 6 vertices, and 7 vertices, and so on. So on phi, this is one of the interesting trees, apart from P5. I think there are only 3 trees. The other one is the K14, the star. So the question was, this was inspired by this analogy. So you exclude 3K1, which is the 3 vertex graph with no edges. Then slightly you generalize and you talk about claw-free graphs. You exclude then the next take a claw and subdivide one of the edges. So what theorems can we push along in this hierarchy? So I conjectured that fork-free graphs are polynomially chi-bounded. And in fact, they satisfy perfect divisibility. That's still open. But what we were able to prove is using additional constraints. If we are H-free for some particular H in a set of 6 graphs, then we were able to prove some structural theorems with Karthik and Kaufman, Jenny Kaufman. And But without any constraints, there was a recent breakthrough which showed that the class of fork-free graphs is actually polynomially chi-bounded. So they cleverly use complete multipartite graphs to prove this. They kind of break your graph into several complete multipartite graphs and see how they interact. And from that, they're able to get a 7.5x squared as a chi-bounding function. But more generally, they were able to prove that T-broom free graphs, a T-broom is just a star with one of the edges subdivided. And they can get a polynomial chi-bounding function for this. So, and recently, Paul Seymour, Alex Scott, and Sophie Sperkel proved that if you are a double forest, which means there are only two internal vertices, there are only two vertices that are not leaves, every other vertex is a leaf, or a star forest, which is just every component is a star, then you're actually polynomially chi-bounded. So that's their latest result in this series. And I'm leaving out a lot of that happens in a geometric setting. The recent nice result was that a big open problem was that the class of circle graphs, are they polynomially chi-bounded? And that was proved by James Davis and Cross McCarthy. They proved that it's actually quadratically chi-bounded. And recently that has been generalized to some other kind of graphs called the grounded L graphs. So these are geometric intersection graphs. And there's rich literature on this topic as well. Okay, so, and so let me give you some questions and problems I think that are worth pursuing. So one question that is the class of P5 C5 free graphs chi-bounded by a polynomial chi-bounding function, in particular x squared. So can you find a polynomial chi-bounding function for this class, in particular quadratic chi-bounding function? So there is no known structural theorem for P5 C5 free graphs. And this class is a generalization of P4 free graphs. So a graph is P4 free. We call it a co-graph. That has sparked a lot of research in algorithmic graph theory, because co-graphs have very nice structural properties and algorithmic properties. So this class is a generalization of that class. So it is interesting to see what properties can we transfer from P4 free graphs to this class. And having a small chi-bounding function is one of the important ones. Okay, and we talked about the odd hole free graphs. The Scott-Seymour theorem says that they are chi-bounded, and this is the chi-bounding function they get in the paper. 2 to the omega plus 2. And so immediate question is, how to convert that to a polynomial, if it is indeed polynomially chi-bounded. So is it polynomially chi-bounded? So are odd hole free graphs polynomially chi-bounded? We don't know the answer. And here is a conjecture that relates the chromatic number, the clique number, and the length of a longest hole. So chi-boundedness is the relationship between chromatic number and clique number. And so this inequality would be a nice addition to the literature if it was true. So you just relate the chromatic number, clique number, and the length of a longest hole. And the rationale behind this is, if L is 4, it works. So the first case, when L is 4, we know if a graph has no hole of a length at least 4, which means it has no holes, that's called a chordal graph. And it's easy to show that they are perfect. Chordal graphs are perfect, which means chi is equal to omega. So L minus 3 is 4 minus 3 is 1, so it works. So even the case L equal to 5, we don't know. So that would be the first interesting problem to think about, which is, so there is a close connection between 2 and 3, problems 2 and 3. Okay, and how about a subquadratic chi-bounding function for graphs with co-girth at least 6, which means the complement has girth at least 6. So in particular, you don't have a 3K1 or a 2K2 or a C5. And quadratic chi-bounding function is known, but how about a subquadratic chi-bounding function? So you're excluding 3 graphs here. Okay, you're excluding 3 graphs, 1 on 3 vertices, 1 on 4 vertices, 1 on 5 vertices. The 5 vertex is the cycle on 5 vertices, 4 vertex is just 2 edges, and 3 vertex, no edges. So this is, I think, the most attackable problem in this list, I think. The list of 10 problems that I'm giving. So, okay, so this is actually inspired from a definition of what is called a weakly chordal graph by Ryan Hayward in the 1985s. And he proved that if a graph in which there is no hole of length at least phi and no anti-hole of length at least phi, then it's perfect. Those graphs are called weakly chordal graphs. So what if we change the phi to a 6? So that's what this question is. So polynomial chi-bounding function in which there is no hole of length at least 6 and no anti-hole of length at least 6. Are they polynomially chi-bounded? We don't know. Okay, my second set of 5 problems is, so there is a natural notion of symmetrization in induced subgraphs, just inspired from Lovaas's theorem. So there is something nice happening with complements. So requiring a graph property for a graph is one thing. Requiring a graph property for a graph and its complement is much, much, much stronger. So if you just exclude P6, we don't know whether it's polynomially chi-bounded, but what if we exclude its complement? Then is it polynomially chi-bounded? So there were recent results about excluding a forest and its complement and showing that they have a linear size stable set or a clique. So there are some nice results on that front. So this process of symmetrization, which is just requiring, in other words, you take a graph class and you intersect with its complementary class. So, and that's also inspired by the perfect graph conjecture. If you take odd hole free graphs and you symmetrize it, you get perfect graphs, which are much, much more well behaved than just odd hole free graphs. And in the same vein, what can we get help from excluding a small 5 vertex graph for the PT free graphs problem? P5 free graph, P5 complement. It's a graph with 5 vertices and 6 edges, and that's called a house in the induced subgraph literature. So if you exclude PT and P5 complement, what do you get? So, and we talked about odd holes, but how about even holes? There is a big literature on this, and it is known that they are chi-bounded by 2x, even hole free graphs have what is called a bisimplicial vertex, which is a vertex whose neighborhood can be partitioned to 2 cliques. So they are chi-bounded, polynomially chi-bounded. But what is the optimal chi-bounding function for even hole free graph? That we don't know. It could be 5/4 of x. So, and here is a structural question about even hole free graphs. Can you take an even hole free graph and partition the vertex set into 2 sets, with each set inducing a perfect graph? This would give a lot of information about even hole free graphs. But this doesn't look very promising, because if so, then the graph it induces has to be a chordal graph, because if it's perfect and even hole free, it has to be chordal. So this is slightly unlikely, but we never know. So I think this is a good problem. And another fundamental conjecture is that the chi-boundedness behavior of a graph class is dictated by its triangle-free members. So you take a hereditary graph class, just put the triangle-free members in the bottom. If the triangle-free members have bounded chromatic number, that's necessary and sufficient for the graph class to be chi-bounded. This is a very, very nice problem, which kind of puts all the emphasis on the triangle-free members of a hereditary graph class. And again, going back to the perfect graphs, an immediate step would be to see if we can extend the success story of perfect graphs by just modifying, going to the next chi-bounding function. The smallest chi-bounding function is chi equal to omega, and that's the perfect graphs. But even if you go to the next one, chi is at most omega plus 1, things get very, very difficult. So a graph, we call it Wiesing if every induced subgraph satisfies chi is at most omega plus 1. And characterizing Wiesing graphs turns out to be a difficult problem. And because the smallest graph that's not Wiesing is on 9 vertices. So as opposed to perfect graphs where there is an imperfect graph on 5 vertices. So finding the forbidden induced subgraphs for Wiesing graphs is a very, very hard problem. But how about we symmetry? How about we say graphs so that both the graph and its complement satisfy this small chi-bounding function. So this is a structural problem inspired by chi-boundedness, by a linear chi-bounding function. Okay. And the final thing I want to share is what I call a super strong Jaffa-Sumner conjecture. So as I told you, the big thing about chi-boundedness, big open problem about chi-boundedness is the Jaffa-Sumner. And this is what it states. For every forest, the class you get is chi-bounded. And remember the Esprit's conjecture, whenever some class is chi-bounded, it is polynomially chi-bounded. That's the conjecture. So if you put the Jaffa-Sumner and Esprit's conjecture, you get the strong Jaffa-Sumner conjecture, which is for every forest, the class of F-free graphs is chi-bounded by a polynomial. So it's strong in the sense that it's chi-bounded in a very strong sense. You have a polynomial bounding function. So I want to propose a super strong Jaffa-Sumner conjecture saying that you can actually chi-bounded by a polynomial whose degree is the number of vertices in your graph in the forest. So no counterexample to this is known. That, well, I mean, that's not a strong argument for the conjecture, but something which could inspire some research on the Jaffa-Sumner conjecture. So the size of your tree appears as the degree of the polynomial in some sense. And where this is known for very few trees. So I think it's just known for stars. The super strong, I think, is known for stars and the fork, right? And the broom. So it's just the stars, and if you just subdivide one of the edges of a star once, it's known. But I think it's open for anything else. This is particularly interesting for P5. And one suggestion would be to work on a weakening of the super strong Jaffa-Sumner conjecture, which is that Scott proved in 1997 that if you exclude not just the tree, but all its subdivisions as an induced subgraph, then it's chi-bounded. So getting inspiration from that, we propose this weak version of the super strong Jaffa-Sumner, which says that if you exclude F star means all subdivisions of F. It's the set of all graphs which are subdivisions of F. So if you take a forest and you subdivide all subdivisions, you exclude all subdivisions as induced subgraphs, then you are chi-bounded by a polynomial of degree given by the number of vertices in your forest. So I think this is more manageable. And that's all I wanted to tell you.
Let's thank the speaker. Any questions? All right, let's thank the speaker again, and we can end the session. We're already over time. Thank you, everybody.
Thank you very much.